Okay, students, so welcome. Today we'll solve few questions based on diffraction of light of engineering physics 2. Students, you can see on your screen where we need to find minimum number of lines on a grating which is resolved for wavelength 5890 and 5896 Armstrong, first order and second order. You can see on your screen we have given wavelength as 5890 and wavelength lambda 2 as 5896. Now we know the formula for resolving power as lambda upon d lambda is equals to lambda divided by d lambda is equals to n into n. Now d lambda is the difference in the wavelength which is 6 Armstrong and n is the number of orders and capital N is total number of lines. So when we substitute the values in the formula we'll get n number of lines, total number of lines is 981. And for second order similarly at the place of small n 1 will substitute n equals to 2 and we'll get the total number of lines on a grating is 491. Let's move towards the next question. Now here we have given a grating which is just resolved two lines in the second order. So we have given n equals to 2. Calculate the grating element. That means we need to calculate A plus B. We have given difference in the wavelength is 6 Armstrong and the wavelength is given 6 into 10 to minus 5 centimeter. Width is given 2 centimeter. So we know the formula of resolving power lambda upon d lambda equals to n into n. We substitute the value and total number of lines will be 500. Now number of lines per centimeter. So it is total number of lines in a centimeter of in a width of 2 centimeter. So number of lines per centimeter will be 250 and A plus B is 1 divided by number of lines per centimeter. So we'll get 4 into 10 to minus 3 centimeter. Now let's move towards the next question. In a plane transmission grating, the angle of diffraction for second order for a wavelength 5 into 10 to minus 5 centimeter is 35 degree. So we need to calculate the number of lines per centimeter. Now for this, what we have given n equals to 2 and number of lines per centimeter is 1 upon A plus B. Now when we use the grating formula A plus B sine theta equals to n lambda, and when we substitute into this, we'll get A plus B as 0.000173 and the number of lines per centimeter will be 5737. Okay, students, so let's move towards the next question. Diffraction grating used at normal incidence for a wavelength 6000 Armstrong. We have given for a blue light wavelength is 4800. The angle of diffraction is sine inverse 3 upon 4. Calculate the grating element. We need to calculate A plus B. Now we know the grating formula A plus B sine theta equals to n lambda 1 and A plus B sine theta equals to n lambda 2. My dear students, for higher order we always get small wavelength. So wavelength, we'll substitute this in the formula and both n lambda 1 equals to n plus 1 lambda by 2. So when we solve, we'll get n equals to 4. Now when we substitute this in the formula of grating formula A plus B sine theta equals to n lambda, let's substitute the value. So A plus B and sine theta is given 3 upon 4 is equals to 4 into 6000. So when we try to calculate, we rearrange this, we get A plus B equals to 4 multiplied by 6000 into 4 divided by 3. And when we solve, we'll get A plus B equals to 3.2 into 10 raised to power minus 6 meter. Let's move towards the next question. The visible ranges for 4000 and 7000 Armstrong. Find the angular breadth of the light first order visible spectrum produced by a plane grating having 5000 lines per centimeter when light incident normally. So we need to calculate the angular width. For this we use again grating formula A plus B sine theta is equals to n lambda. Now for first wavelength we'll write the same formula as A plus B sine theta 1 is equals to n, and wavelength will be 4000 Armstrong, and Armstrong will convert in centimeter, will be 10 to minus 8 centimeter. A plus B is given. A plus B is 1 upon number of lines per centimeter, which is given 6000. Therefore sine theta 1 is equals to, order we have given 1, 4000 into 10 to power minus 8 divided by 0.166 into 10 to power minus 3, 0.166 10 to power minus 3. Therefore theta 1 will be sine inverse 0.2409, which is 14.41 degree. Similarly, for wavelength 7000 when we calculate, instead of wavelength 4000, when we substitute 7000 we'll get theta 2 as sine inverse 7000 into 10 s to minus 8 divided by 0.166 into 10 s to minus 3. When we solve, we'll get this as 24.94 degree. Therefore, angular width theta will be theta 2 minus theta 1. 24.94 minus 14.41. So angular width theta will be 10.53. Let's move towards the next question. Find the maximum order of grating having 5500 lines per centimeter. Wavelength is, so we have given A plus B is 1 upon number of lines per centimeter, which is 5500. We have also given wavelength is 5896 into 10 to minus 8 centimeter. Now to convert for maximum order sine theta, we take 1 for order as maximum order. Therefore grating formula will become A plus B sine theta is equals to n lambda, or A plus B is equals to n lambda, or n equals to A plus B divided by wavelength. So when we substitute the value, we'll get 1 divided by 5500 multiplied by 5896 into 10 to minus 8, and when we substitute, when we calculate this, we'll get n equals to 3. So maximum order is 3. Let's move towards the next question. How many orders will be observed by grating having 4000 lines per centimeter? if it is illuminated by light of wavelength 5000 and 7500. So we'll write the grating formula. We have given number of lines per centimeter. So we have given A plus B is 1 divided by 4000. Now for wavelength 5000 Armstrong, I can write this formula. Grating formula is A plus B sine theta is equals to n lambda 1, and n will be maximum when sine theta is 1. Therefore, the maximum order will be A plus B divided by lambda 1. We substitute the value 1 divided by 4000 into wavelength is 5000 into 10 to minus 8. When we substitute the values in formula, we get n equals to 5. Similarly, for second wavelength, A plus B sine theta is n lambda 2. Therefore, n equals to A plus B divided by lambda 2. Let's substitute the details. So 1 divided by value of A plus B same 4000 multiplied by 7500 into 10 to minus 8 centimeter. We'll get this as equals to 3. So the range is from 3 to 5. Let's move towards the next question. A plane transmission grating. Observed light wavelength. Find the highest order spectrum. So let's find out the highest order spectrum. Use the same formula. A plus B is given 1 upon 5000, and we need to find the maximum order. Wavelength is given 6000 into 10 to minus 8 centimeter. So we'll use the formula A plus B is equals to A plus B sine theta. A plus B sine theta is equals to, and lambda order will be maximum if I take sine theta as 1. Therefore, when I substitute into this formula, we'll get n equals to A plus B divided by wavelength. Value of A plus B is 1 upon 5000 into 6000 into 10 to minus 8. When we substitute the form values, we'll get n equals to 3.33, or n is equals to 3. Now in the same, we need to find the missing order. So question says that the opaque space is twice of transparent space. We know the formula A plus B sine theta is equals to n lambda for interference maxima. A sine theta is equals to m lambda for diffraction minima. We'll divide A plus B sine theta with A sine theta is equals to n lambda divided by m lambda. Sine theta cancel. Wavelength get cancelled. We have at the place of B we'll substitute 2a. So this will become 3a divided by a equals to n upon m. A cancel. N equals to 3m. We'll substitute the value of, so n equals to 3, 6, 9, and other higher order values are missing interference maximas. Plant transmission grating of for second order principal maxima. So we have given n equals to 2. Theta is given 30 degree, and wavelength is given 5 into 10 to minus 5 centimeter. Calculate the number of lines per centimeter. So we need to calculate a plus b, which is 1 upon number of lines per centimeter. So we use the grating formula a plus b sine theta is equals to n lambda. So a plus b is equals to 2 into 5 into 10 to minus 5 centimeter divide by sine theta, which is sine 30 degree. Sine 30 degree is 0.5. So we'll get 4 into 5 into 10 to minus 5 centimeter, or 20 into 10 to minus 5 centimeter. So number of lines per centimeter is equals to 1 upon 2 into 10 to minus 4, or 10 to 4 into zero point 0.5, which is equals to 5,000. Therefore, number of lines per centimeter, number of lines per centimeter is 5,000. Thank you, students. So these are all possible questions from the chapter Diffraction of Light.